This is Learning Python Data Analysis, published by Pack Publishing. I'm Ben Hoff, and this is Section 3, Scientific Computing with Numpy and SciPy. In this section, we're going to take a look at array features, bucketing arrays using the digitize and histogram functions, simple aggregations, and linear algebra. So let's go ahead and get started. For this series, we're going to switch to using Jupyter Notebook. Jupyter Notebook is basically Ipython, but in the browser. I know all the folks who don't use the terminal as much are probably celebrating right now. So in order to activate virtual Jupyter Notebook, we're going to go to the command line and making sure that our virtual environment is activated, run the command Jupyter Notebook. Now for me, this will automatically open up a new window, but if that doesn't work for you, the Jupyter Notebook will actually tell you where it's running at, what the address is, like right here, http://localhost and then 8888. So from here, we're going to get a list of folders and files starting at whatever directory the Jupyter Notebook command was run from. We can open up files and folders if we want. So let's go ahead and change into this data analysis folder real quick. We probably want to start in the new dialog. So you can see we can make a text file, a new folder, a terminal, or a Python 3 notebook. So let's go ahead and start with the terminal real quick. And let's see which Python we're using the which Python commands. So you can see here, we're still using the Python activated in our virtual environment. So if you're doing some analysis and you figure out that you don't have a package installed that's new, this is a good way to actually get that installed using the pip command. So if we go back and we go to the running tab up here, we can actually see everything that's currently running in our Jupyter Notebook session. So note, you can see this terminal right here. Let's try to close out that tab. And what you can see is this actually doesn't close out the terminal instance. If you want to do that, you actually have to manually hit the shutdown button or close it out from the actual terminal using either the Control-D or the exit command. So going back to the File tab, the most useful new selection for us is actually going to be the Ipython Notebook. So let's go ahead and start one of those using the Python 3 kernels. So full disclosure, if I suddenly start sucking at typing, it's because I'm married to the Vim key bindings and not used to coding any other way, so bear with me. But let's go ahead and get started. So the first thing that we're going to do is actually create a bunch of new tabs here using the A key. Perfect. And then we'll go ahead and import Numpy as NP. In order to evaluate this cell, we need to hit Control-Enter. Because if we hit normal enter, it'll just start a new line. And then Shift-Enter will actually open up a new line if you need it. So any variables that are assigned or things that are imported aren't dumped into the program scope until it's run, which is important if you open up someone else's already completed notebook and try to execute in the middle of the notebook without running all of the previous cells. It won't work. Trust me, I've made this mistake a lot. So moving away from my failures and back to Numpy, what does Numpy give us? Well, according to the documentation, Numpy is used for homogeneous multidimensional arrays, fast mathematical operations over arrays, linear algebra, Fourier transforms, and random number generation. What does all that mean? Well, let's back up to the array bit. Homogeneous multidimensional arrays. So homogeneous means that all the elements in the array need to be the same type. So no mixing integers and strings, for example. Multidimensional means that we can have more than one axis. In more Pythonic terms, more than one axis really means arrays can be lists of lists. So let's demo homogeneous and multidimensional arrays real quick. So if we wanted to make a homogeneous array, we just need to make sure that all of these have the same type. Like for example, in this one, they're all integers. For a non-homogeneous array is also pretty easy. So we would just need to make sure that we mix the types, right? So say we put in a couple of integers, and then we put in a float, and then we put in a string. So this is non-homogeneous. We've got mixed integers, strings, and floats. For a multidimensional array, remember, this is just a list of lists. So we're going to create a list on the outside that's going to encompass, and then on the inside we'll actually create a couple of lists inside of it as well. Perfect. So these are all Python lists right now, but let's go ahead and demo creating Numpy arrays. So the easiest way to make an array is actually to call the array function, and we need to pass in a list in here. I'll show you why we need to do that in a second, but we'll just go ahead and create a list that contains 1, 2, 3, 4. And you can see that returns back our 1, 2, 3, 4. So what won't work for us if we don't pass the numbers in either a tuple or a list, Numpy is actually going to give us an error. And let's go ahead and check that out real quick, right? So we get this value error. The problem is the function is expecting either a list or an iterable. So we need to make sure that we pass in either a list or a tuple. One way or the other, it doesn't matter which, but we need to make sure that it does that in order to be successful. Cool, so what about our multidimensional arrays? Well, don't forget we can also pass in previous types as well, so we could actually just pass in that multidimensional in directly, or we can go ahead and create our own array, the array of array functions. So this would be a manual array of arrays, just like that. So obviously we don't want to create our arrays manually every time, so Numpy offers several methods for creating common arrays. So for example, if you're just trying to get a list from like 0 to 10, the easiest way to do that is using the arange function right here, and you'll get your list from 0 to 9. I forgot. So the way this actually is if you don't import any of these variables, these are basically equivalent. So let's go ahead and show that, the equivalent here. So the equivalent is you can pass in a start, a stop, and a step number. So these two function calls are the equivalent of each other. And if you don't pass in any of the other numbers, it'll just assume that you want to start at 0 and you want a step of 1. You'll also notice that it doesn't go up all the way to 10, but it does include 0. So in this function call, we include the start number, and then we don't include the stop number. So that can be a little bit tricksy if you don't know that. So if we wanted a different step, like let's say we just wanted to do even numbers, for example, we could do that very easily by passing in a step of 2. Now, up to this point, all these have been integer arrays. So how do we work with floats? Well, there's actually, if you want to work with floats, there's a different method, and it's called Linspace. And it's the same thing, right? So we pass in a start number, we pass in a stop number, and then we pass in the amount of points that we want along the space. So instead of a step, we pass in the number of points we want. So we want 6 points, and that'll divide in between those two numbers 6 times for us very conveniently. Now, if we're just working with stuff and we just want some values, but we don't care what they are, the rand function out of the random module is a good way to do, is to get some random values here, and we'll just pass in and get out an array of 3 random values from 0 to 1. With this function, we can also get multi-dimensional arrays. So for example, if we wanted something with 3 rows and 2 columns, we could just pass in those variables and get those out. A couple of other useful arrays that you might end up creating quite frequently would be like an array of ones. Similarly, the zeros array is also very useful. And lastly, the I function is very useful. And what this will do is it'll actually put a 1 on the diagonal, and then everything else will be 0. So this is the identity matrix, which can be very helpful. So Numpy also supports some advanced slicing for multidimensional arrays. If you're not familiar with slicing, slicing is a fast way to get a subset of data. For example, when I was writing code to fetch the retweet and favorite information for our tweets, one of the Twitter API calls would only accept a maximum of 100 tweet IDs per call. So I had a list of 10,000 rows, and the challenge was to iteratively grab out 100 at a time, and the best way to do that was to use slicing. So let's go ahead and make a list of 1,000 random numbers. So we'll just go ahead and call this my list, right? And we'll use the random module with the rand function, and we'll get a list of 1,000 random numbers. So if we look at this real quick, we can see that is indeed a large list with a lot of values in it. Perfect. So the slicing syntax, if you're not familiar with it, it uses the array accessor brackets, the semicolon, and anywhere from 0 to 2 numbers. So let's go ahead and demo that real quick. We'll just actually just pass in the semicolon for this one. And what we'll get is actually a view of the whole list back. Now notice I said a view and not a copy. So if we make a change on this variable, for example, so using Ipython, right, we know that the last result is stored in the underscore. So let's just go ahead and set the 0 index equal to 0. And it's originally, what is it originally? 0.036. So it's originally a different number. And then if we look at the my list, or the original data member, what we'll see is that first number is now 0, right? So it's important whenever you use Numpy to know that slicing returns a view and not a copy. Anywho, so let's get back to the actual slicing context, or the slicing syntax, excuse me. So if we wanted to grab out the first 100 items of an array, the full up nomenclature to do this would be 0, semicolon, 100. And if we look at the length of this array, we can see the length is actually 100. So the number on the left-hand side of the semicolon indicates the first number that we want to grab, and the number on the right-hand side of the semicolon indicates the last index that we want to grab. So you can also specify a step index, for example, if you wanted to grab from the first 100 items, but you only wanted to grab every other one. You add another semicolon and then add your step number in, and that'll actually help grab every other item, for example. And we can see this using the length attribute here. And another easy way to use this syntax is you don't actually have to pass in any sort of numbers. So for example, if you just wanted to grab every other type of every other item out of the row, you can just put 2 semicolons and then your desired step size. And if we look at the length of this, this should be 500. Perfect. And then another easy thing to do is you don't have to pass in either the left hand or the right hand side of the information. So let's say you wanted to grab the last 300 numbers. You could actually say you want to start at 700 and you want to go to the end of the list. And if we look at the length of this, it should be 300. Or if you wanted to grab the first 200, you could actually do the reverse of this, where you don't pass in that left-hand side, but you do pass in that right-hand side. And that'll go ahead and grab out the first 200 numbers of this database, or first 200 numbers of this data. So the more interesting thing with Numpy is we can actually slice multi-dimensional arrays. So for example, if we make an array that is 5 by 5, we can actually use the slicing syntax to grab out a 3 by 2 array. So you can see we've grabbed out the first 3 columns and the, or excuse me, so you can see we've grabbed out the first 3 rows and 2 columns of that array. So the multi-dimensional slicing is really useful when you want to take just a chunk of an array. So other than multi-dimensional slicing, what other advantages do Numpy arrays have over Python list? Well, it all comes down to efficiency. A Numpy array has a much smaller memory foot compared to a Python list. So according to this Stack Overflow question, where they had a 100 by 100 by 100, or a million data points, the huge difference here, especially when they scale, because one of the questions they asked was actually, so what if I have a 1,000 series, which is a billion floating points? The difference really is in the memory. So if we had a billion cells using NumPy, it would end up taking about 4 gigabytes, but to use Python with the same thing, with the multi-dimensional list of lists with Python, you'd take 12 gigabytes. So that's an 8 gigabyte difference there. So once you're working with really large numbers, it's really useful to use Numpy because it's so much more efficient on memory usage. The other thing is Python lists also don't support vectorized operations like Numpy does. such as element-wise addition and multiplication. So what do I mean by vectorized operations? Well, let's go ahead and demo those. But first, let's do this demo on our actual Twitter data. So let's go ahead and get access to that really quick. And I'm going to use pandas for convenience. You could actually do this using the SQLite module as well. It's just going to be easier for me to use pandas, so we'll do that for convenience. So we'll go ahead and use the same read SQL method, and we'll get both our tweets, and we'll pass in the URL, and we'll also get our users using the read SQL method by passing in the users table and our URL. Now, in order to get out the actual Numpy array from the pandas data frame, the thing that we have to do is call the asMatrix command. So if called on the data frame, you can actually specify which columns you want in the method call. So in order to get some data to manipulate, let's go ahead and grab the hours that our users were created at and convert it over to a Numpy array. So we'll say hours is equal to users dot created at, and we'll use the datetime module to get the actual hour, and then we'll get it as a matrix. And if we look at the type, we can see that we've actually got a Numpy array. Now, the asMatrix command is useful for when it's being called on the data frames, but for series, such as this hour attribute is actually a series, we can actually just use for series, we can actually just use the values attribute. So if we do this again using just that, we get the same thing, which is hour dot values, which is a bit of a quicker way to grab that data out. So we can actually look at that data member. As you can see, we've got quite a bit of data because we've got this ellipsis in here, so that's working just fine. All right, so now that we've got our data, let's go back to our element-wise addition and multiplication. So you can do all the normal mathematical operations on arrays, and they will operate on every single element in the array. So for example, if we wanted to add 2 hours to all of our created at, you can see that that works. We could also subtract 2 hours. We could multiply. We could divide, and we could also do exponentials, right? So let's say we wanted to take everything to the 1.2 times power. Well, we can definitely do that. So let's look at some of our types, remembering that the data types in Numpy all have to be homogeneous. So we can check the data type of the original array using the dtype attribute, and we can see that's an int64. So let's look at the data type for the output of our exponential operation. So we'll get the 44th cell output, and we'll call the dtype attribute on it. That's interesting. It's a float 64. So what happened here? Well, Numpy automatically upcasts values to be more precise. So if we needed to, we can always downcast variables afterwards. So if we did a bunch of mathematical operations and we ended up with a float 64 and we needed to put it back into our database as an int, we can do this using the asType method, passing in the actual data type that we want. So for our case, we'll call the asType and pass in and say that we want it back as an integer. And that'll work just fine. So if we don't want to operate element-wise, we can also operate on multiple matrices with Numpy. Matrix-on-matrix operations are the specialty of linear algebra. Linear algebra is insanely useful. As an engineer, I can tell you there are a lot of systems and equations that can be modeled using linear algebra. If you're not an engineer, a good way to motivate linear algebra is to think of it as a way to put together a lot of input through a very particular set of transformations. You can use numbers, matrices, and positioning to represent the transformations. So the diagram from this website does a great job of explaining how it works visually. Here we go. So on our right hand side, we've got input data. In the center, we've got a bunch of operations that we want to perform. And on the right hand side, we've got our output data. And the way that this graphic visualizes it is, imagine taking the data from the right and pouring it through these center operations and putting them then, once they come out from this operation, on the left-hand side. And so we take our first data set and we pour it through all the operations, and we take the result and put them all right here. And then we take our second data set and do it again and put the output right here. So that's very useful, but let's actually look at what an example of this looks like. So we're going to skip past the rest of this blog post, which I highly recommend you reading if you're interested in it. And let's do an example, which is a stock example. So stocks are volatile, and these are no different. On the right, we have input data, which represents a stock portfolio containing stock in Apple, Google, and Microsoft. Each column represents a different portfolio. In the center, we have the volatility, or adjustment, to each portfolio.